share. Okay. Do you see my notes? Are they visible?
Sir.
Yeah. Okay. So I am now all set except that I have to wait out. Recording has also started. Very good. But there's 1 minute for the lecture to begin. So I should wait for people to.
Sir, may I ask you something?
Yes. Follow.
So what is the definition of discrete topological subgroup, sorry.
Discrete topological subgroup is a subgroup on which the induced topology is discrete.
Okay.
So it's a subgroup make it a topological subspace and ask whether that topological subspace is discrete. Then you will call that a discrete subgroup.
Okay,
and any
sir.
such thing in a Hausdorff group is closed, is what we proved.
Yes, sir.
Okay. All right, it is time, so let us begin. Hello, guys, and this was the last lecture. Let's quickly go through the last lecture because today's lecture is a continuation of the last lecture. There is no hard and fast division between last lecture and this lecture. We started talking about compactness, and we said compactness is a generalization of the notion of finiteness. But also, there are some very important basic compact sets, namely closed and bounded subsets of the Euclidean space. So all compactness is modeled after these. Then we looked at the definition of compactness for a topological space. It said that a topological space X is compact if given any open cover, which means X is the union of all those open sets. These are subsets of X. Then finitely many of these UIs are enough, and X will be the union of finitely many of those. Then we said that though this definition is totally topological, if X is a metric space, if there is a distance given to you, then there is a lot more that can be said about compactness. Therefore, we are studying compactness for metric spaces in yesterday's lecture also today. This you learn, you get the hang of it by solving exercises. That's the best way of understanding this. And a very good collection of exercises on compact metric spaces or in general on metric spaces are in Kumareshan's book, Topology of Metric Spaces. Compactness is chapter 4. Go look at the exercises there and solve them. Now, the starting theorem of this subject is that the closed interval is compact. Any cover has a finite subcover. That we proved by the 20 question method. Every answer you give cuts down the possibilities by half. Now we focus on that half and ask a question which will again cut down the possibilities by half. And then you zero in on a single possibility by going on doing it more and more and more infinitely often. There's no magical number 20. You keep making it smaller and smaller. Okay. So that was the 20 question method. And by that we showed this closed interval 0, 1 is compact. Why does not the 20 question method work to show that the open interval is compact? After all, when you cut the open interval, it also becomes smaller, half the size. So why doesn't it show that open 0, 1 is compact? Bolo.
Because you need not get that unique point. You need not get a point inside.
Correct. Because this produces points closer and closer and closer to each other, which means a Cauchy sequence. That Cauchy sequence need not converge in open 0, 1. Okay. So we showed how to use the method skillfully for I cross I also by making one cut vertical, next cut horizontal, next cut vertical, next cut horizontal. That is what ensures that the leftover portion becomes the portion on which you're focusing becomes smaller and smaller and smaller. And you can do it in higher dimensions also. So what is the yes no question you ask? Does the interval have a, is there a finite subcurve for all of it? Yes, done. No, okay, cut it in two. Is there a finite subcurve for either of these pieces? If both yes, then you put that together. Therefore, there is at least one no. Take that no wala in interval and cut it in half and so on. This is the method. And then we said, Hein-Borel theorem, every closed and bounded subset of a Euclidean space Rn is compact. That's because any bounded subset is contained in some big cube I to the power n. And because it's closed, now it's a closed subset of a compact space. And every closed subset of a compact space is compact. That's the exercise we did here. We said that given an open core of C, add one more open set, namely x minus c. Now it becomes an open core of x. So as a finite subcore. Now you can leave out this fellow, and the remaining ones will give a finite core of that subset C. Then we said if xd is a metric space, an important point there is Hausdorff, and C is a compact subset of X, and C is closed in X and bounded with respect to the metric. So one of you gave this argument saying, okay, take a point outside. Now given any point of C, they are separated by non-intersecting neighborhoods. Do it for every possible point. You will get many neighborhoods here and different neighborhoods here, many neighborhoods of the same point P. Finitely, many of these open sets suffice to cover C because C is compact. Take the intersection of the corresponding open sets, that's that red set. Now that red open set is disjoint from C, showing that the complement of C is open. That was the proof. We asked converse, what your converse meant. If something is closed and bounded in a metric space, is it compact? And the answer was no. After all, an infinite discrete metric space, meaning the distances are always 1 or 0, all of it is closed and bounded in itself, but because it's infinite, it's not compact. Because each point is an open set, and that open core has no finite subcore. So we proved this, X be a Hausdorff topological space and C a compact subset, then C is closed in X. This proof is actually a topological proof. Then we started looking at equivalent formulations of compactness. I told you that compactness is very important, and it occurs in many alternative versions, and you should be able to recognize those versions. And once and for all, prove equivalence between various versions. Therefore, in any context, if you recognize one of these properties, you also know the other properties hold there, without trying to visualize how the other properties look in that context. So some of these properties are here, but there are a whole lot of properties possible. So one of them says that every sequence has a convergent subsequence, and the other one says every infinite subset of X has a limit point. Actually, I realize I never explained to you what's a limit point. Let me do it here. Let X be a topological space, a subset, X belongs to X. And X is called a limit point of A if every punctured neighborhood of X contains a point of A. What's this punctured neighborhood? Punctured neighborhood means you take a neighborhood, actual neighborhood U, open X. This is a neighborhood. The neighborhood of x in X, open neighborhood, means something like this. People also use the word neighborhood to mean anything which contains an open neighborhood is also a neighborhood. Anyway, doesn't matter. Punctured neighborhood is this x minus u minus x. This is a punctured neighborhood of x, which means this is how u looks, and this is where x is. You remove x, and rest of it is a punctured neighborhood, punctured disk. And if x is a limit point, means points of A keep coming closer and closer to that point. So in order to avoid some point, you take an even smaller neighborhood. Then to avoid some point, you take an even smaller neighborhood, etc. Provided these points are closed. In Hausdorff space, all these points will be closed. So you can avoid those by going smaller. But in that smaller punctured neighborhood, there is again. And why punctured? Because it may be that x itself belongs to A. We are not going to call it a limit point unless other points are coming closer and closer. So it's not true that every point of A is a limit point. That's not how we say. Some points of A are limit points, some points are not. If I take the real line, every point is a limit point of real numbers, because there are other real numbers, sequence of other real numbers which is tending to it. In a discrete space, no point is a limit point because there are no other points tending to it. So those were examples where A was equal to X. Okay. So for a metric space, we said that the following are equivalent. That's why I talked about limit point. Every infinite subset of X has a limit point. This is equivalent to every sequence in X as a convergent sequence. And then if every infinite subset of X has a limit point, then that means X is complete and totally bounded. Excuse me, I have to answer a phone call, unfortunately. What is this? Yeah, sorry about that. Now, the claim is any this is complete and totally bounded, and you guys were giving me various proofs, but let's recall what was total boundedness. Total boundedness means take balls of any prescribed size, finitely many of them will cover your space. That's total boundedness. And he motivated it by saying that the center of the ball is the mobile tower, and the radius of the ball is the radius of effectivity of the tower. So you want to cover your country or city or whatever it is by mobile towers, so that every point is within that given radius of the tower. Can you do it with finitely many towers? Yes, if the power of the tower, if the radius is very large, you can do it. But for every radius, can you do it? And that's the question of total boundedness. So you were given these exercises. Totally bounded implies bounded is the converse to any subset of totally bounded is totally bounded, blah, blah, blah. And 4 implies 1. If X is complete and totally bounded, then it is compact. This was done by 20 question argument. You had various open balls, finitely many covered them, and then given an open cover. Does it cover these balls? Which is the one that it doesn't cover? Now take smaller and so on. So you were asked to play with these properties yourself and sit down and try to write implications between something and something, something and something, something and something, till you end up showing it's all equivalent. And then if you are ever going to write a book, you may think of arranging them in some cyclic manner so that the proof goes here to here, 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 here. So n different implications are enough instead of n into n minus 1 implications that you will have to prove if you don't have any such particular path. But the n into n minus 1 implications give you far more insight than that cyclical way of proving. Because let me draw a picture to make my psychological point. Here's my psychological point. Okay. Suppose the n different statements are this. And you are directly proving the equivalence between each one of them. Then you are ending up making a figure like this, etc., etc., and so on. This is n into n minus 1 connections, because the implications have an arrow. This implies this implies that, and whatnot. While the cyclic one will look like this. You will arrange them like this, and you will say first one implies the second one implies the third one implies the fourth one, and so on, fifth one. And then minus 1 will imply that. Now, if you want to prove that 2 implies 1, you can't go like this. You have to go all the way, which means you have to remember all those intermediate stations and all those intermediate arguments, and then you have proof of this. If you are going to write it once and for all and write a book, that may be the shortest book you will produce. But when you are actually thinking and working, you are not going to remember all those things. And then to go from here to here, you have no direct intuition, which is why if you draw many more arrows, then you have better intuition of things. And so I explained this to you, and I asked you to indeed play with these. So now let me ask, have you guys been playing with these statements and trying to prove them yourself? Yes or no? Am I audible?
Yes, sir.
Yes, okay. So have you been trying to prove some of these implications?
Yes, sir.
Very good. Maybe right now you are too busy, but I don't know what too busy means. It's like mathematics has to come to your mind when you're doing nothing. Automatically it comes. That's the default thing you think about when you are not occupied by any job like fill this form or go buy some eggs or whatever. Whenever you are not busy doing such things, it should automatically just be mathematics. And when you are not asleep, of course. Anyway, so keep toying with these, and it's not the spectator sport. But if you try very hard, you can look at a book, any of the books. They're all pretty similar, and they all have different tricks. But then close it and try to do it your own way, and try to write down your argument so you remember it. Okay. Now, one of the equivalent formulations of compactness was that every continuous function from x to r is bounded. What is the proof of that? That if it is compact, any continuous function is bounded. Why? So let's write down the proof of that. X compact.
Because
Yeah, implies
yeah,
bolo.
the image of fx is compact, so it's closed and bounded. I mean the image fx,
Correct.
not image of
Correct.
fx. Sorry.
Yeah, image fx. Therefore, fx is bounded. We are not bothered about closed here. Huh? But the interesting thing is, if it is not compact, then it admits some unbounded function. So if every function is bounded, then f is compact. And the proof was depending on what is called the Teize extension theorem, which we will address at some point, probably Monday or Tuesday, I don't know. Oh, I don't think I have lectures on Monday or Tuesday. Whatever. Like the next or the next lecture, we'll do these things, because we also have to do Ascoli-Arzela theorem. These are two things we have to do. Okay. plus the following exercise. So let's at least address this exercise. If a metric space is not compact, show that there exists a countably infinite discrete closed subset, which means the induced topology on D is discrete. One of you was asking some time back what is a discrete subgroup. A discrete subgroup is one on which whose subspace is discrete. As a subset, it is discrete. So if it is not compact, show that there exists a countably infinite discrete closed subset. How will you prove such a thing? So look at these various things which are in terms of limit points. This says every infinite subset of X has a limit point. So you are going to produce an infinite subset which has no limit point. Yeah. And then is that subset discrete since it has no limit point? Yeah. Suppose I have a subset of a metric space and suppose that subset has no limit point. Then is it discrete? Yes or no? What a spelling, D-I-E. Yeah, somebody is willing to tell me if I have subspace. So this is the question I'm asking you. Answer. Let X be a metric space. Let A X be a subset such that A has no limit point. Is A discrete?
Yes, sir.
Yes. But here you are asking for something more. You are asking for infinite discrete closed subset. How will you produce a countably infinite discrete closed subset? Yeah. So solve this exercise. Once you solve this exercise, and how will you solve this exercise? You know that what is there in compact, and therefore one of these statements is false. Okay. Perhaps you think of sequence which does not have any convergent subsequence. So will that subsequence, so will that sequence be a closed set? It has no convergent subsequence.
Yes, sir.
Yes. So you have to look at these various properties. Once you play with them, things occur to you that, let me try this or let me try that. And then when you have produced, yes, is A closed? Not necessarily. Okay, the other approach is let Xn be a sequence in X which has no convergent subsequence. Is the set of points Xn closed? Is it discrete? And you would say both answers are yes. Once you produce such a set D, which is an infinite discrete closed set, now you proceed as follows. So here's my metric space X. Here's this D, which is an infinite discrete closed set. So it has a countable infinite subset. So let those points be called xn, or well, these are, and D is the set of all these xn's. Now define a map from D into R. Meaning xn goes to n. This is continuous. Why? Yes, because D is discrete. So I got a closed subset and a continuous map. The Titze extension theorem says that this map you can extend to a map on all of x. Okay? And once you extend it on all of x, I have a continuous map on x, which restricts to this map on this closed set, and which is not bounded because it's taking every possible natural number value. So that's why this is equivalent to the earlier one. Modulo the Titze extension theorem, that we will do. Then in yesterday's lecture, I asked you to determine the automorphisms of the Euclidean plane, distance preserving automorphisms. I only want to introduce one concept to help you. Exercise. Or this is a definition. Let P, Q, R belong to this plane R2 such that dPQ plus dQR equal to dPR. How do they look? How will such points look? Tell me.
This triangle.
Will they look like a triangle?
I think they will be on the same line.
They will look like a straight line, right?
And they will
That's,
look straight line.
that's the whole point, that there is equality here. Usually this is greater than or equal to, yeah, that's a triangle inequality, right? Triangle inequality says this is greater than or equal to, because it's a triangle. But the special case of triangle is when they are in straight line. So they look like this. And now what can you say about, what about D, FP, FQ plus D, FQ, FR? What is that equal to? Remember, F is a distance preserving map from R2 to R2. So what is that equal to?
It is D of FP differ.
FR. Why? Because this is equal
Line
to
gets
dPQ, and this is equal to dQR, and this is equal to dPR, because it's distance preserving, and this plus this is this. That's what you are told. Therefore, this plus this. Therefore, these 3 points, wherever they end up, FP, FQ, and FR, they are again on a straight line. This is why lines go to lines, because if I take the line determined by 2 distinct points P and Q, then all in-between points exactly go to in-between points on the segment. And you can also show it for points on the other side, because then you can take that point as the other end and this as one end, and then in-between points will also contain that, etc. And that is why you will conclude, you will be able to answer what will F do to straight lines. The next question is, what does F do to angle? Suppose I have some angle. And suppose this is 41 degrees. Okay. Now I take FP, FR, and FQ. And you know this line has gone to this line, and this line has gone to this line. What is this angle? What do you think?
I think it's the same.
And why is it the same?
So I can tell you how these maps are, the Fs that you
No, no,
want.
no, no, no. Haven't you been to school? So there is this R, there is Q join and make a triangle.
Okay, congruence. Yes, yes. Okay.
This is just congruence of triangles.
Yeah.
You see, Euclid based his whole idea of congruence on these rigid maps, as I was telling you, right? Euclid said that take distance preserving automorphisms of R2. Two figures are congruent if the image of one figure is another. All this he says in his Euclid's Elements. All the in-betweens, college teachers, school teachers ignored it because they didn't understand group and automorphisms. Actually, they didn't ignore it till NCRT came on the scene and destroyed mathematics. Well, this is a very strong statement. They didn't destroy everything. So let's say till they came on the scene and destroyed whatever was traditionally being done and replaced it by the latest fad from USA. Till that event happened, and it happened around 1970. Generations of school children were basically taught from Euclid. In India, the standard school textbook till independence was perhaps Euclid. Afterwards, various school boards were set up and various authors wanted to write books and make money. But and the same thing happened in America, and the same thing happened in other advanced industrial countries. But let's say about 1900, the standard textbook in all schools was Euclid's Elements. And they used to say that Euclid's Elements, because every school child had a copy of various volumes, was the most printed book in the world at that point of time. And the second one came Bible. So Euclid was printed even more than Bible in 1900. You can check these things by going to Google and asking appropriate questions. Anyway, so automorphisms were what everything was based on. And as you know, Galois was talking of automorphisms of field extensions. And as you know, Minkowski and later Einstein got converted. All these guys started talking of automorphisms of space-time, and they called it Lorentz group and whatnot. And so everything was about group actions and automorphisms and invariants and etc., etc. Representation theory, etc. And then for in between time, all this was forgotten. But now, well, hopefully it will all come back. I don't know. Okay, so I have given you the hint on how to solve this along with some historical gyan. And now let's come to today's lecture, which is continuation of what we are doing. So if x and y are metric spaces and f x to y is a map, you know what is meant by continuity at a point x of x. That means given epsilon greater than 0, there exists delta greater than 0, such that dx x prime less than what? Delta implies d fx fx prime is less than epsilon. Have I written it correctly? I hope I have not made a mistake in writing this. Okay. So it is continuous at a point. Continuous means continuous at every point. Every point. Every x. Given epsilon, the number delta can depend on x. And uniformly continuous means we can choose the same delta for all x. In other words, given epsilon greater than 0, there exists delta greater than 0 such that d of x1, x2 is less than delta implies d of fx1, fx2 is less than epsilon. for all x1, x2. So I want to test your knowledge of this. So is y equal to sin x uniformly continuous? Same
Yes,
delta
sir.
uniformly works. So was that Sonakshi?
Yes, sir.
Yes. Okay. I hope you can prove it, but let me pass that for the time being. Is y equal to x square uniformly okay? Is y equal to x uniformly continuous?
Yes, sir.
Yes. My next question is, and I have to put it in blue here, is y equal to x square uniformly continuous?
No, sir.
No, sure. Why not?
Sir, it will be uniformly continuous on any closed interval, but not on
That's
R.
right. On a bounded closed interval, yes, but on R what happens? So let's look at the picture of this. The picture looks like this, okay? And you see what is happening is, within the same interval, here it is increasing somewhat. And within that same interval, here it is increasing hell of a lot. How fast is it increasing? That's the derivative. Dx square by dx equal to 2x. So as x increases, it rises faster and faster, and therefore for a tiny change of x, okay, so as you know, delta y is equal to f prime x times delta x approximately. Approximately it is this. And so if f prime at x becomes larger and larger, for the same change in x, there's a hell of a lot of change in y. So you cannot have the uniform delta working for everything. Okay. Next question. If f from R to R is bounded, is it uniformly continuous? This thing was clearly unbounded, so it can change quite a lot. So suppose it is bounded, is it uniformly continuous?
Take sine 1 by x.
Sine 1 by x is not a function from
Yeah,
R
I
to
know.
R, is it?
I'm modifying it. I'm adding something. And at 0, we define it to be 0.
Is that continuous?
Oh, God. But you have not put anything on continuity.
No, I have put it continuous.
Yeah.
Have I not? Okay, so is okay. So good, you're right, and let me put where did I say continuous is what is saying? Bounded and continuous. Okay, now I have said it. So tell me, if f, so what's your answer now?
But I think even if that's okay, we can ignore the 0, 1 point and we can stretch. So we can define it on open 0, 1, where it is continuous, and stretch it via homeomorphism.
No, uniform continuity, the deltas will change by stretching. Yeah? You cannot replace the real line by open 0, 1. These are metric spaces, and the distance matters here. These are distance preserving. We are talking here of distance preserving maps. This is in the category MET DP. All this is happening in the category MET DP. That's why right in the beginning, I grounded you on what are the different kinds of things one does with metric spaces. Okay, now, so tell me, Ishan, don't give up.
Not yet. I mean, I do not know yet.
Okay, let me draw a picture. Yeah. Hello?
Sir, the answer is no.
The answer is no. Okay, right? We are perfectly democratic. You say answer is no, well, that's an opinion, but you have to back it up.
Sir, take an example, sine x square.
Sine x square, wonderful. So here is an example. Sine of x square. And how does it look? You see, it starts oscillating faster and faster and faster and faster and ever faster. See, this is what is happening. You try its derivative. What is derivative? Yeah, tell me what's the derivative?
So 2x into
2x cos x square.
2x cos of x square. I trust you. Now, take a number such that when is cos x, so take for example root of 2 pi n, right? Take this x equal to this, xn equal to 2 pi n, root of 2 pi n. Then what is cos of x square? Cos of 0 is 1, no? Yeah.
2 root 2 pi n.
So this is equal to 2 times root 2 pi n, which is very large. The derivative gets larger and larger at certain points. It's not uniformly large because after all it does turn down again. That's why you have to so choose x so that this number becomes 1 when this number is very large. And then from the derivative, you can see that in a tiny interval, it's going to vary a hell of a lot. Okay. So this is not uniformly continuous. Ishan, okay? Good example? Good.
Yes, I was thinking of this picture, but I did not remember the function.
So it was very nice. The student who gave this example not only had the right pictorial intuition, but she also produced a formula. And you have to be able to do both, have the intuition and produce a formula. Okay, good, very good. Now, my question, if next proposition, I have written a proposition here. If X is compact, then any continuous map is uniformly continuous. Yeah, nice.
Yes, it is true.
Proof?
Yeah. Can I have a minute or maybe?
No.
Okay, I mean, there's one way using the Lebesgue number, but that makes me think of a proof of the Lebesgue number. But we can do it otherwise also, which is
it's a very obvious.
It's a picture, but
yeah,
but I don't know how to describe.
So all of you think about it. See, many proofs are possible. See, all this thing, because you see there are so many properties equivalent to each other in this. Each one may have his own or her own. See, my language is stuck in the old habit of saying his. So his includes her, which is a bad idea. Could I say her? But then, this now we are becoming increasingly sensitive to these issues. And even practically on the ground, you see lots of young women mathematicians. There weren't so many women mathematicians earlier. That number is also monotonically increasing, and then gradually the culture will change, I hope. Okay. So each one can have its own proof. Okay. So somebody willing to describe a proof? Chalo.
Yeah. And the thing is, if you want to cover, so let's pick an epsilon, okay?
Yeah.
And corresponding to that, you get a bunch of deltas. And those deltas form a cover. So those delta neighborhoods will form a cover of.
And you want a Lebesgue number for that, unfortunately. Anyway, so let me give a proof. Here's a proof. Okay. So for suppose it's not uniformly continuous. Suppose not. F is not uniformly continuous. That means, see, the negation of for all epsilon means there exists some epsilon for which the opposite is true, right? So there exists some epsilon greater than 0 for which no delta can work. This is what it means. Because to be uniformly continuous means given any epsilon, you can find a delta. Not uniformly continuous means there is some terrible epsilon, terribly small maybe, for which no delta can work. So let's try deltas one by one. Delta equal to 1 does not work. Therefore, there is some x1 and x1 prime. So that d of x1 prime is less than 1, but d of fx1 prime is greater than epsilon. Well, let's try perhaps delta equal to half. That also doesn't work. So that means there is some x2 and x2 prime, which is less than 1/2. But d of f of x1 prime is still greater than epsilon. Well, let's try delta equal to 1/3, and again the same problem. You will have some x3 and x prime 3, and their distance is less than half, but the distance between their images is still greater than epsilon. So I have these two sequences. One is x1, x2, x3. It may be jumping all over the place. x4 may be here, and x5 may be there, x5, and x6 may be here. But you know, where is x1 prime? It's within distance 1 of it, x1 prime. x2 is within distance half of x2. x3 is within x3 prime is within distance 1/3. And x4 prime is within distance 1/4. And x5 prime is within distance, and x6 prime is very close, x prime 6, distance 1/6, and so on. Now, if X is compact, then this sequence has a convergent subsequence. Okay. So, end of the argument goes like this. If X is compact, Xn has a convergent subsequence, and limit P, let us say. And Xn prime also has a convergent sequence. Now, take that corresponding subsequence. If I have convergent subsequence, I simply take the corresponding one. The corresponding subsequence of x prime n, see, those points are coming closer and closer to these points, and these points are converging to something called P. So those points also converge to P, also tends to P. Okay. Now what? Now, because both of them come closer and closer to P, okay, how can the distance, and the map is continuous, P has some image Fp. So because they come closer and closer to P, their images are in that tiny neighborhood of P. Then how can they remain epsilon far apart? They are getting closer and closer. Contradiction. Understood? Yeah,
Yes, sir.
anybody? Huh? Yeah. Very simple pictorial proof. Just by trying to prove just take the opposite statement, try to prove it, and we use nothing but the definition, no tricks. We just used sequential compactness. So we used compactness in one of the equivalent forms. Instead of this open cover subcover, we used this equivalent formulation of compactness. So it's important for you to know such equivalent formulations of compactness, because depending on the context, one of those formulations is going to be easy and useful and not the other, as this example showed. So let's come here. Yeah. So now we introduce the most important concept of an equicontinuous family. You are having a side-by-side complex analysis course. Are there equicontinuous families there? Clearly not, otherwise you would have said yes, but you'll encounter it perhaps later, next week, next week, or in a subsequent course. So let me introduce the definition of equicontinuous. But before that, I wish to make some comments about uniform continuity, etc., etc. So, okay, let's come to that. So suppose X and Y are metric spaces, yeah, and F is a set of continuous functions from X to Y. So here is X, here is Y, and you have a set of continuous functions. Okay, I should not draw X as a bunch here. I should rewrite my picture. Otherwise, it looks like I'm sending points. No. Okay. So so here is X, here is Y, and a whole lot of maps from X to Y. This is the set F. It's a set of maps, all of them continuous from X to Y. Okay. Now this equicontinuity is a property of F, and you say F is equicontinuous at point X, at a point X in X, if given epsilon greater than 0, there is delta greater than 0, so that for all F in F and X prime in X, we have this less than delta implies this is less than epsilon. So you see, what is equi about it? This is just continuous. If there was a single function, then this should just says it is continuous at X. Equi means the same delta works for all functions in the family. For all these functions, I have common delta. So let me ask you, let's take R to R, and my family of functions is X goes to X, X goes to X square, X goes to X cube, etc., etc. This is my function F1. Fn x equal to x to the power n. So I have a family of functions. F equal to a set of all Fn. Is this equicontinuous? Tell me. है या नहीं? So difficult? Draw pictures. One function looks like this, x to the power 0. Next function looks like this. Third function looks like this. Fourth function looks like this. They start rising steeper and steeper. Because they start rising steeper and steeper, to keep their derivatives tend to infinity, right? Let's say if I take its value at say x equal to 10, the derivatives are tending to infinity. And therefore, to have that same variation by epsilon, my delta needs to be smaller and smaller and smaller and smaller. So each higher power is going to need a smaller delta at x equal to 1 or x equal to 10 or whatever. And if x is less than 1, I am not going to get a problem. But if x is greater than 1, I am going to get a problem. Again, I will get a problem on the negative side beyond x equal to minus 1. Okay. So this is not equicontinuous because the delta I get depends on f. So it's as if saying that it's kind of uniformly continuous in the functions. Instead of uniformly continuous in the domain, this is uniformly continuous in the function. It's a kind of uniform continuity where you are varying the function. So you understood the definition of equicontinuous. Any questions on equicontinuous? Okay, there is none. Now I'll introduce a double uniformity. So that's called uniformly equicontinuous if both things happen. So it says that given any epsilon greater than 0, there is some delta greater than 0, such that for all x and x prime in x, we have df, distance between x and x prime less than delta implies d, okay, for all, okay, for all f in f. So given epsilon, I get my delta. That delta doesn't depend on where I am in x. It also doesn't depend on which function. That same delta works for all functions, and same delta works for all functions is equicontinuous. And same delta works for all x and x prime. Okay. Double all. One all here, one all here. This all is all over x. This all is all over the family of functions. So this double uniformity is called uniform equicontinuity. One of them is called equi, the other is called uniform. Equi is when you are varying the function. Uniform is when you are varying the point, because uniform continuous function is when you vary the point. So have you understood the definition of uniform equicontinuity? I hear a chorus saying, yes, yes. What do you take us to be? Get on with it. Okay, yes, yes. Now, so here are some exercises, very trivial exercises just to test whether you have followed the definition. If a family of functions is uniformly equicontinuous family, then any subfamily is uniformly equicontinuous. If a family is equicontinuous, then a subfamily is also equicontinuous. True? It's like saying that I have uniform, if I have continuous function on a metric space, its restriction to a subspace is again continuous. If I have uniformly continuous function on a metric space, its restriction to a subspace is again uniformly continuous. So same thing being done now in the function direction also. Equicontinuous, uniformly equicontinuous in both directions. Then a singleton set f, meaning a single function. What does it mean that a single function is equicontinuous? Don't mean anything, because you cannot vary f at all. But uniformly equicontinuous means f is uniformly continuous. So again, this is a family of continuous functions. Yeah, continuity I'm all the time assuming, unless otherwise said. Now, if X is compact, then any equicontinuous family is uniformly equicontinuous. I want you to do this exercise. Does it remind you of an earlier exercise? The earlier exercise for which I showed this picture of how I have one converging sequence and the other sequence all the time getting closer to it. So the other also converges to the same point, and therefore the successive members of the two sequences come closer and closer and closer. And because they come closer and closer and closer to the limit point, their images also come closer and closer and closer to the image of f. Therefore, they come closer and closer to each other by triangle inequality. Therefore, they can no more satisfy this, and therefore contradiction. This was the proof that on a compact metric space, any continuous map is uniformly continuous. This is the double version of it. If X is a compact metric space, then any equicontinuous family is uniformly equicontinuous. The equicontinuous is taking care of uniformity in varying the function, and uniformly is to take care of varying in X. And the varying in X argument I already told you. So you are supposed to combine those two, that argument with the definition of equicontinuous, and show that any equicontinuous family on a compact space is uniformly equicontinuous. Okay, I don't want to spend the remaining 4 minutes doing this because I'll get nowhere. Instead, I'm going to jump and I'm going to introduce to you the projective space, because I saw from your WhatsApp things a lot of chatter about projective space. So here is, I'm going to introduce to you the projective plane. The projective plane as a topological space. This is how you do it. You take a sphere, that sphere is S2. Okay, this is how S2 looks. And now I am going to say that a point in S2, this is a point, each point has an antipode. This S2, as you know, sits inside R3, right? This sits inside R3. It's defined by the equation x square plus y square plus z square equal to 1. Now, given any point, it has an antipodal point. Join it to the center and go to the other side, and you will end up with a point minus p. Okay. So if p was xyz, this is the point minus x minus y minus z. Minus the vector. This is a vector, and this is minus the vector. Understood? Every point has an antipodal point. This introduces an equivalence relation on S2, under which P is equivalent to P and also P is equivalent to minus P. This is an equivalence relation. And the quotient S2 mod equivalence relation is called the projective plane. Another way of saying the same thing. Okay. I have the group, multiplicative group, plus minus 1. This is a group G. Okay. This is isomorphic to Z mod 2. G acts on S2. How does G act on S2? Some element of G is lambda. Lambda is plus minus 1. On P is equal to lambda P. So if lambda is equal to 1, then lambda P equal to P. If lambda equal to minus 1, then lambda P, lambda acting on P is minus P. So you understand this is a group action. Is it clear? And then the quotient is to mod this group action is the plane, projective plane P2. This P2 is the name for the projective plane. Projective plane is called P2, just as affine plane is called R2. So have you understood what's the projective plane? Now let me describe its points in another way. Suppose I have a vector subspace, one-dimensional vector subspace of R3. What is the one-dimensional vector subspace of R3? A line through the origin, right? So L in R3 is a one-dimensional vector subspace. I want to ask you, what is L intersection S2 equal to? Tell me.
2 points.
Only 2
There will be
points.
only 2 points because these are unit vectors on the line. On a line, how many unit vectors are there? Well, from the origin, if you go to on one side, there's a unit vector there, and opposite side is the other one. And what are those two vectors? They are plus minus each other, right?
Yes, sir.
Here, L is equal to all multiples of P. That's all. So P is a basis for L. Minus P is another basis. It's one-dimensional. So a single vector generates it. So where it intersected the sphere was the P. And where it intersected it again was minus P. These are two opposite points. Okay. So somebody drawing a three-dimensional realistic picture would have showed a dotted line. So let me show a dotted line. This is minus P, and then dot, 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 dot. All these parts are inside this, and this is the origin, O. So therefore, any such pair of antipodal points, that is to say the orbit of the group, exactly determines a line, because now given any pair of antipodal points, just take the line. And so you can say that as a set P2 equal to the set of all lines through the origin in R3. This is another way of viewing the projective plane. This you can do with any vector space. Given any vector space V is any vector space over any field. Okay. Then you take P of V to be the set of all one-dimensional linear subspaces L of V. There we are talking of an arbitrary field. We are not talking of any topology, but this is the analog of what will happen in real numbers. What happens in complex numbers is very interesting because instead of a single unit vector, now there's a circle full of unit vectors on the line. And so it's a quotient by a certain action of S1 rather than by plus minus 1. Okay. All right, so I have run out of time and we are at the end of this week, number 4. And I was tempted to talk to you about projective spaces because I just watched some WhatsApp before this lecture and saw a lot of chatter about projective spaces. So anyway, because I didn't have enough time to go into the Ascoli-Azela theorem, which was what I would have done had I enough time left. So Ascoli-Azela theorem goes to next week. And so I'm going to end. Any questions?